let's go for part 3, considering that we have 8 parts today. So, so thinking about that, yeah, we need to be kind of save energy for the rest of the parts that we have for 6 parts. When we talk about assessments, let me just kind of in part 3, I'm going to give you a better sense about the variation of assessment tools that we have. When we talk about assessment and cognitive assessments, what are the different assessment tools we need to consider? When we talk about assessment, we need to think about something structured. What do I mean by structured? We discussed about RDoC before. And RDoC is a good example of a structured assessment framework. So we try to define different categories, different levels of assessments, and trying to navigate the process based on the very well-defined kind of framework. Think about, okay, now I assessed this. These are assessments for negative valence, there are assessments for positive valence, there are assessments for social. So I try to have a structured assessment. And then the question is, can we have what we call deep assessment? And deep assessment means that having multiple assessment for each individual subjects, trying to have better assessments over the time. So that is what we call deep assessment. And it is always the case to have an assessment which is going to be time efficient. So we do not have endless resources. We need to be careful about the timing. And timing is always a significant issue. And contextual issues are also important in terms of the environment and how, as Atif was asking about, in terms of how we consider contextual factors, environment, early life, childhood, stressors and adversity, how we consider those factors as contextual factors. And then we like to have assessments being unified. I mean, unified of using the assessments the same way that I'm using the assessments here in Tulsa, Oklahoma, to the assessment that people are using in Tehran, Iran, people are using in Ankara, Turkey, in Abuja, in whatever city or country we are talking about. How we can unify assessments to have the same tools and same assessment across different labs. There is a project, it's called Phoenix. And right now here, at least in US, if you want to have a project, for example, in the field of substance use disorder, we need to consider the kind of Phoenix as the basic assessments to make sure that labs across US would have the same structure in terms of the baseline assessments. Then we can share databases and we can cross-talk about the assessments that we are doing. There are specific batteries for assessments that different groups put together. For example, this one is from NIDA. It is a structured one. As you can see, they have defined different categories and different major constructs that should be assessed. And then they try to find different tasks. For example, in the field of cognition, this is a specific task that would take 5 minutes. So you need to think about time. Time is always critically important. You need to think about how much time each task is going to take. Otherwise, I mean, you would be out of resources that you have for the project that you have. So different domains, different instruments. You need to think about all these things together when you talk about assessment. You cannot be a cognitive neuroscientist without having a good understanding about the assessment tools that are available in the field. So you need to know about the assessment tools that are available in different dimensions and how you can assess different dimensions with different assessment tools that you have available. And as you can see here, we usually have a timetable of how much time these assessments are taking, and we need to be really careful about how to use these tools. And for each project that you are running, you need to have these assessments, and you need to have a clear idea about, based on the questions that you have, what are the assessments that you need to take into account. But as a cognitive neuroscientist, most of the time we are interested to know about neuroimaging-based assessments. So we need to, and we like to bring neuroimaging to the assessments that we have. This is also the case for a project that we call UK Biobank. So they started with people of 500,000, so 500,000 people in UK. and they started to do lots of assessments, biological assessments, but they realized it would be nice to add neuroimaging to that as well. So they considered a project to do neuroimaging among 100,000 of these people. And you cannot imagine how it would be complex in terms of doing imaging in 100,000 people. So think about how many scanners you need to have to be able to do 100,000 scans, even if you want to do it one time. And if they want to do it every 5 years, they realize that if they use the scanners with the best possible timing during the day and doing something like the entire day scanning, they need to have 7 scanners working 7 days per week to be able to do these scannings and be able to repeat that every 5 years. So now they have 7 scanners across UK doing these scans, and they are providing these databases publicly available. So they had to decide what are the measures that they need to consider. They decided to have resting acid fMRI, some task-based fMRI, diffusion or DTI, and structural MRI. Okay, and this protocol is taking, I think, around something like 34 minutes to acquire these images, and they realized that every single 1 minute then they add to this project, that would add something like £1 million extra cost to the project. So if they just want to add 1 minute to this imaging protocol, that would cost them £1 million. So they need to be really careful in terms of how to optimize the timing of these scanning protocols. Otherwise, I mean, that would be waste of time and resources. So they have done that. And then the question was, okay, what are the specific measures from these databases that are going to be important? In a traditional way, neuroimaging was being used as a tool to show us, okay, there is a, let's say, abnormal tumoral tissue here, or we have a significant level of atrophy here. So, I mean, the ventricles are larger than normal, and we have a level of atrophy here. So, this was the way that we have been using neuroimaging before, and we have been calling them as clinically meaningful phenotypes in imaging. But what we are thinking about, okay, these are the clinically meaningful image-derived phenotypes that we have been using before, but now we know, I mean, based on things that you have learned in this cognitive neuroscience class, you know that we can kind of extract many other measures from the imaging databases that we have. So we are looking for some other image-derived phenotypes from the measures that we have. And in the ideal case scenario, we'd like them to be automated. So we like to have analysis pipelines to put those images inside those analysis pipelines, and then think about kind of specific analysis pipelines to measure, for example, frontoparietal connectivity and the connections within default mode network and connections within whatever measure that you are thinking about that would be potentially clinically meaningful to be automatically extracted from database as quantifiable or quantified biomarkers, as we discussed about before. So that is something that people were trying to do. In the first step, they decided about 39 image-derived phenotypes from the structural MRI. For example, the volume of head of caudate, the volume of putamen, the volume, so all those major volumetric measures from structural MRI. Or from DTI, they measured something like 600, more than 600 measures. For example, the thickness of track between dorsolateral prefrontal cortex and amygdala. That could be one of those image-derived phenotypes from DTI. So they measured 600 of them. And then in the task-based fMRI, which was the face task, we have discussed about that before in terms of having happy and neutral faces and trying to match them with the reference face. We call that hierarchy task. Trying to measure the task-based fMRI data from task-based data that they collected. And in the resting state fMRI, they had over 1,700 measures. And for example, the frontoparietal connectivity would be one of these 1,771 image-derived phenotypes. So you can imagine the size of that. And thinking about, for example, the resting state fMRI, they have tried to find different networks and then connections between these networks, as you can see here, and then the level of signal that they have within each network as well. So considering both activities in each network and also connections between networks with these complex correlation matrices between these networks. So, and this is how they ended up having 1,700 image-derived phenotypes just from resting state fMRI data. So you can see, and as you can see here, they have not selected a specific connection. So they have done something like a data-driven exploration to extract whatever data that they can extract in the simple automatic analytic process, and then they try to say, okay, now we ended up having these measures. How we can measure their clinical validity? Okay. They also had 1,100 health-related factors in terms of, let's say, lifestyle, alcohol use, physical characteristics, cognitive phenotypes. So they had all those, let's say, health-related factors. And those 2,500 IDPs in 6 categories that we discussed before in terms of T1, structural, task-based, DTI, resting state, both amplitude and netmat. Netmat, it means connections, and amplitudes means the level of signal that they have within each network. Okay, so they had all these measures. So you can imagine they started to make a correlation between all these 1,100 health-related factors and those 2,500 IDPs, and finding is there any standing out correlation between these automated measures and health-related factors to find those which are going to be clinically meaningful for us. So that is what they have tried to do. And you can imagine about the size of the correlation matrix that they made. To be able to visualize that, they use what we call a Manhattan plot, trying to show each of those correlation pairs, one health-related, one imaging-related, to one single, let's say, circle here. So this one is one health-related factor and one imaging correlated to each other. And this is the p-value, the log of p-value of the correlation between these two measures that will be reflected here. Okay? And as you can see here, they are being categorized based on these 11 health-related measures. Okay? And this one is about amplitude, and this one is about connection strengths within the resting state fMRI. So this one is a correlation matrix of 1,100 health-related factors and something like 1,700 resting state fMRI related factors would be reflected to these figures. As you can see here, there are image-derived phenotypes from resting state fMRI that are related to health-related factors. And these are the p-values of really small p-values, as you can see here, which are reflected here. So, and they are mainly towards the physical characteristics, as you can see here. I mean, they are the most important factors that are reflected here. For example, in terms of the cognitive phenotypes, this line shows the corrected p-value threshold for all these comparisons that they have done. As you can see here, in the field of cognitive, there is almost nothing that would pass this threshold, as you can see here. And there are things that are close to that, but nothing here. If we had something here, a cognitive performance was significantly related to a specific, let's say, connection in the brain, or here it was related to a connection, but they didn't find anything that would pass the multiple comparison threshold, so they didn't have anything here. And those features are related to mainly physical features that you can see here in general. Okay, the level of head motion inside the scanner. The question we had was about whether there is any relationship between the level of movement that the people make inside the scanner and their physiological, or let's say their psychological characteristics. So we have been thinking those who are more impulsive, they might kind of move their head more, and those who are not, they could remain inside the scanner still because they have, let's say, more calm characteristics or personality. So we have been trying to work on that. Why? Because motion is an important factor in terms of the level of measurements that we have in fMRI, and many measurements that we have are they could be highly related or highly correlated to motion. For example, especially when we talk about connections or resting state connectivity measures, they are highly correlated to motion. So we try to do in data analysis, we try to remove the effect of motion. But in reality, we cannot completely remove the effect of motion. There is always a residual effect of motion in analysis that we do. Okay, is there any relationship between kind of psychological features and motion? Because if there is a correlation between these two features, as we know, and we cannot remove that effect from the database, there is always a level of, let's say, contamination in the database because of the personality characteristics. What we found was basically just physical variables were able to explain something like 10% of the variance in the motion data, in the head motion data inside the scanner. Okay, I mean by physical variable, I mean weight, BMI, the different body composition measures in terms of, let's say, fat mass in the body, all things related to the physical features. So these physical features were kind of describing or explaining something like 10% of the variance inside the database. We have done that with psychological variables, and we realized that something like 5% of the variance could be explained by that. And those factors were mainly related to substance use, alcohol use, even impulsivity. I mean, all of those factors are, they do make sense. Those who were more impulsive, they have been using nicotine, probably they had a level of nicotine withdrawal, they have been moving more inside the scanner, okay? And then we realized that, okay, if we add all variables together, whether they are physical variables, and then all the psychological variables. And by psychological variables, we had 100, something like 40 different questionnaires and assessments. So it was a really intensive assessment. And we have something like close to 500 subjects. It's a really large database. We realized that we can just explain kind of around 11%. So it's close to what we had just with physical variables. So we realized that technically, whatever we have in psychological variables in terms of predicting the motion was shared with physical variables. So we just removed the effect of physical variables from psychological variables. And we realized that if we remove those factors, we can just explain something like 1% of the variance with psychological variables, if we remove the effect of physical variables. So eventually we realized that physical variables are critically important in terms of the level of motion that we have inside the scanner. And then when you go back and see the results that we saw before, then you might start to think about, okay, now these correlation, high level of correlation, could be related to motion that are related to physical characteristics of these people. So not quite sure that they are really talking about clinical features. So you still need to think about that. But that is the idea of attempt that people try to use these huge imaging databases and find specific characteristics in these databases that are related to health-related factors, trying to find a clinical meaning to whatever we are doing. And it is challenging. It is not simple to do. There are complexities for that. And that is the start of the second part of my talk today, which I'm gonna give you a better sense about the complexities that we have in the field of cognitive neuroscience and the complexities that we are gonna face and try to solve together for the next couple of decades that we are gonna be active in the field of cognitive neuroscience.